feel. Lay on the out and out, preach your words and verbs, and act academic sermons. Come along with me, take my hand and do some learning.
Welcome. Let's do some math. Today we're going to talk about some of the fundamental concepts involved in topology. Now, topology, like many areas of mathematics, has a variety of sub-areas, but when you start learning topology, there are sort of two paths to consider. One through point set topology and the other through geometric topology. We'll look a little bit at both in this video. Let's get started. It's worth comparing geometry to topology. In some sense, geometry can be thought of as a rigid subject, whereas topology can be thought of as being squishy. Sometimes I like to describe topology as squishy geometry. That is, things are more flexible in topology. Now, in geometry, because things are so rigid, you have a lot of data. When you're looking at a given object, if you know everything there is to know about that object, you know things like area, volume, angles, distances between points in the object, and so on. Topology tracks less of this information, so there's less data, which means if you have a given object, you know less about it. But that can oftentimes be more useful because you're not restrained by the rigidity of geometry. You can say more fundamental things about a given geometric object. In geometry, it's very rare that two objects are the same because they have to have so many geometric criteria satisfied. Their volume has to be the same, surface area has to be the same, all the different angles of the object have to be the same. There's a lot that needs to be the same in order for two geometric objects to be considered the same. Topology, on the other hand, many objects are the same. You would take objects that look initially very different and say, in fact, they're the same if they satisfy fundamental topological criteria. Now, the first thing we'll look at is polyhedra, or individually called polyhedrons. Typically, a polyhedron is thought to be made up of three sets of objects, differing in dimension. The first objects would be vertices, which is just a collection of points. The next set of objects would be edges that connect the vertices. And then finally, filling in the area between the edges are faces. This would be a case of a tetrahedron, which has 4 faces, which has 6 edges, and which has 4 vertices. But there are many different types of polyhedra. Looking at two different polyhedra, such as a tetrahedron and the cube, we might say that the surface area of this tetrahedron could be √3 square units, while the surface area of this would be 6 square units. Likewise, we might have a volume in cubic units for the tetrahedron here, differing from the volume here of the cube, and so on. The number of vertices are different, the number of edges are different, the number of faces are different. And just a shout out to all you nerds who are watching this video, of course, we're looking at a D4 with the tetrahedron and a D6 with the cube. In fact, all of the traditional gaming dice are platonic solids with the exception of the D10. That's not, but it's still a polyhedron. Now, if we look at this, basically nothing is the same as far as these geometric quantities. Surface area, volume, vertices, edges, faces, all different. But yet, though in a geometric sense these are different, I make the claim that topologically these are exactly the same. They are identical from a topological point of view. Remember, topology is squishy geometry. There's more flexibility there, which means less has to be the same, yet you can still call two objects the same, and that's because we're looking at more fundamental properties in topology. Now, so far we've said that these two are topologically the same, but
what if I told you
that everything I'm about to show you is in fact the same topologically? This one is also the same. This one is also the same. As is this. As is this. Looks like a beach ball or basketball. As is this. As is this. These are all the same objects. You have now taken the topology red pill. If we extend this classification, we've said that these objects are all the same. It's also true that all of these objects are the same. And in some sense, these objects are the same. I make the claim that topologically these are identical, and these are not identical, but they are defined by a single number. That is, there's a number that we can assign topologically to these, that is all the same between them, to these, that is all the same between them, and to this that's the same between both of them. Do note that these are all surfaces, as are these. This is a surface, a one-sided surface, hence it's non-orientable. And this is a one-dimensional type thing. There's something called isotopy, or continuous deformation. Suppose we start with this inner tube looking thing here. What you can do is you can bend it and you can stretch it. So you could stretch it out and bend it around like this. So you could go from this object here to this object. This is all valid when we say we're doing isotopy. What is not valid when we say we're doing isotopy is you cannot cut it. You cannot glue it. For instance, we can't take this middle part and sort of, paste it to itself. You can't glue things together, and you cannot self-intersect. So again, continuous deformation and isotopy, we can take this weird inner tube donut thing, we can bend it and stretch it out. That is covered under isotopy, but again, the things that are not covered under isotopy are cutting, gluing, and self-intersecting. Now let's look at a bunch of objects and see if we can determine how they relate to one another under isotopy. Here are a whole bunch of objects, all surfaces, so they're all two-dimensional. I claim that certain pairs of these objects are the same. Not all of them are the same in the topological sense, but some pairs are. It could be that these two topological spaces or objects are the same in a topological sense. Or maybe it's that these two are. I'm not claiming they are for sure. I'm just saying there are pairs of objects in this array of different surfaces that are the same. As an example of what I mean and how we can continuously deform or isotope one shape to another, I claim that this object in the upper corner here and this object here, the double inner tube, I claim these are the same. Now, at first blush, that should seem ridiculous because these two are linked, as we can see, and yet these are somehow not linked, the two different kind of donut parts. But let's see how they're in fact related under isotopy. We start with the object that we had in the top left, the sort of linked double donut with this arm stretching around. And just to keep track of things, we're going to color part of this object as green. That's going to make it easier for us to track what's happening, so we can sort of track the green band and help us focus our eyes on what we should be looking at. So let's start by taking and saying, well, you can stretch this out. So we can take this hole by the green band and we can sort of stretch it, which has the effect of doing something like this. So we've taken this hole, we've stretched it out, which is pretty cool. Now, there's nothing saying we can't keep doing that. So keep doing it, and now we get to this point. Again, let's keep moving this thing over until we get to here, where it's kind of on the side that's towards us. What was originally this part, we now have this attached to it. And we just did that by kind of sliding this green arm around until we get to here. Now we're going to move this part around and behind so that we get this. And now we've moved it around, behind, and sort of in front. Now with it in front, we'll continue to pull it till we get to here. We'll clean this up a little bit by pulling this in. That is kind of shrinking this arm here. And then finally, we'll do a little bit more shifting around and we get to this here. All we did was bent and stretch this thing around. We did not do any cutting. We did not do any gluing. We did not do any self-intersection. We used isotopy to move from this object to this object. In the topological sense, if you can move from isotopy from one object to another, we say that those are the same topologically. There's various ways to say that objects are the same topologically, but this is one way, via isotopy. Going back to that list, we've now said that these two objects are the same, under isotopy. The claim is there are other pairs of objects such that they're the same under isotopy, and maybe you can determine what those are. It's a pretty fun activity to do. Now, with all that we've done here, one may ask a valid question, which is, where is the rigor here? Mathematics, especially pure mathematics, is often defined by its rigor. And here it seems like we're just kind of drawing things and pushing them around. And sometimes, even high-level mathematicians, especially high-level topologists, will draw very intricate diagrams, and that's a large part of what they're doing. However, there is a lot of mathematics behind it. the place you really start getting formalism is through point set topology. Here you learn about the fundamental concepts of topology in general, things such as connectedness, compactness, continuity, things we'll look at. And then you can branch out into other topics where you tackle topology in different ways. There's three main branches. First one being differential topology. This is somewhat like analysis. You do many of the similar things you would do in analysis. You can do algebraic topology. That's very much like what we've seen in abstract algebra, but you're applying it to topological spaces and you have sometimes a little more flexibility. So using the techniques of algebra to explore topology more, and sometimes vice versa. And then finally, geometric topology. This is the most quote-unquote topology of topology. Sometimes called cut and paste topology. This is where you're working with diagrams the most and doing all this really complicated mathematics via diagrams. And sometimes those diagrams can get incredibly complex. Or you can even have simple diagrams that represent things that are hard to understand themselves. As I mentioned, differential topology involves a lot of analysis and linear algebra. Algebraic topology is really just a lot of abstract algebra applied to topological spaces. And geometric topology, cut and paste topology, you see other fun things like surgery theory and Kirby calculus. But it all stems from point set topology. If we have a set X, we can define a topology, in this case we'll denote it tau, on X, and it's a collection of subsets of X. So you always have a set X, and then the topology is a collection of subsets defined on that set. So you really need a set to start with, and then you look at subsets to define the topology. Now, that collection of subsets needs to satisfy three properties. The first property is that the extreme sets, that is the empty set, and the set that has the most things in it, compared to X, which is X itself, that must be an element of the topology tau, or the collection tau. Another property is that if you have a pair of things in tau, if you have two subsets, then the intersection must also be in tau. So for any two things, if they're in tau, the intersection also has to be in tau. Finally, if you have any collection of things in tau, or any subset of tau, said another way, the union must also be in tau. Now notice there's a difference between 2, which says you have to have a pair, or says at a base level you have a pair, and saying in 3 that any collection, it could be an uncountably infinite collection of things. It does not matter. Any single collection, you must have that the union is also in tau. Then if you have this collection tau of subsets of X that satisfies these three properties, then in that case, what we say is the pair X tau together form the topological space. And you can have a set with different topologies defined on it. And when you define different topologies on it, even if you have the same set, you would still consider those to be distinct topological spaces. So take the real line, I can define very easily two different topologies, and we would say those are two different topological spaces. Now, of course, this is abstract, like many things that we've looked at here, so let's go ahead and look at an example to try to ground this definition a little bit. Let's say we have a relatively simple set, X, which has 3 elements in it. Now, there are various subsets of X. The simplest subset of any set is the empty set. Then there are subsets with one element in them, sometimes called singleton sets. Then if we scale it up, the 2 element sets in this particular case would be like so. And then finally, the only 3 element set that is a subset of X is going to be just X itself, the set containing A, B, and C. These are all the possible subsets we could have of X. Say we have the empty set, the set containing just A, the set containing A, B, B, C, and then X. Let's go through and check the properties of this collection and see if it fits the properties of a topology. The first one being that 0 and X, the parent set, this X here, should be in the collection. We see that they are, so we're good to go there. It satisfies the first property. Then we ask ourselves, what about all intersections of elements of things in here? Now, we're not computing all the intersections of all the elements, period. We're just looking at intersections of elements that are in this. And now, You can check them individually. The intersection of A with the empty set is the empty set, which is in here. The intersection of A with AB is the set containing just A, which is in here. But then if we look at this intersection, the intersection of AB with BC, there's only one element shared by these two, B. So their intersection is the singleton set B. However, we do not see that intersection in this list here. Therefore, the second property of what it means for a collection to be a topology, that is not satisfied. And once one of the properties is not satisfied, we say that it's not a topology. We need them to all be satisfied. Let's say we consider another set X, and this one has an extra element D in it. But now we'll define the collection on this set X to be tau2, and it contains these subsets of X. If we go through and check the properties of topology, the first one is the empty set in X in this collection. Yes, they are, so that's good. What about the intersections of pairs of elements? That's where the previous collection had failed to be a topology. But if we go through and check in this case, we will indeed find that all the intersections between pairs of elements in here are also in here. Now with unions, if we go ahead and we look at the union of, let's say, this triple of sets, the union of the set containing A, set containing B, and the set containing BC would be the set containing ABC. But we do not see the set containing ABC in this list. So as it is, this is not a topology on X. Now note, if we make a slight adjustment here, we will get a topology on X. Let's say we go back to what we originally had of ABC being our set X. If we do so, now we find that the union problem we had before of these sets, ABC, is now just the set X. So if we have this X, now it's the case that this will be a topology on X. So the set X you have and the collection are very important, and you need to be able to satisfy these three things here. Now there's a term that we use in topology to indicate particularly important subsets in a collection. Simply the things in the topological collection. All of these sets we call open sets. All it means to be an open set when you're talking about a topological space is that it's in the topology, that it's in the collection. In this case, we have the set X, it's in the collection as it will always be when we're looking at topological spaces because it's a criteria. That's an open set. So is the empty set in this case and will be in every case. It doesn't have to be here, but this singleton set happens to be an open set because it's in the topology. So does this one. It happens to be an open set because it's in the topology. This set, it's in the topology, so it's an open set. And then finally, this is in the topology, so it's also an open set. Open set means to just be in the topology, and that's it. With that, I hope you enjoyed this video and learned something. We'll see you in the next video.